Well, maybe people drift in and people can catch up, so maybe you just start. We're 5 minutes early. But we were making the point last time that we're interested in open channel flows. The thing that's different to them from closed channel flows is not the fact that it's not in a pipe, because you could have a half-filled culvert, and that would be an open channel flow, even though it would have a roof to it. But the issue, I guess, is that you have this free variable in terms of the free surface, and from continuity, you know that if you draw a vertical line anywhere along this, you know that the same volumetric flow rate, Q, has to be going across it. The downstream portion has a deeper depth, and so the cross-sectional area is larger, so the velocity for the same flow rate has to be slower. And so the flow can self-organize into a very fast, shallow flow upstream, or a relatively slower, deeper flow downstream. And so we'll actually visit that today. We talked last time about uniform flows, where by definition it wasn't allowed to do that. It has to stay at the same depth upstream and downstream. And maybe we'll just finish that off by looking at a very quick example. And then after that, move on to talking about gradually varying flows and rapidly varying flows, which are what these are. So that's our deal today. So if we go back to this, okay, I'll actually show this again. This is, I absconded from another year's 303 class. This was probably in November of 2014, I think. And so this is a stream coming out of the southern Alps in south of France. The Alps are like the Canadian Rockies in western Alberta, are all metasediments. They're limestones largely. And so this is a stream coming out of limestone, beautifully clear, as you can see, from a spring. As you might know that things like limestone, well, we have limestone around here. All the water supply for State College comes out of limestone. We have these lineaments, which are faults and big fractures in the limestone that are fractured and have big high permeabilities. They may run for hundreds of feet, thousands of feet, and so they have a large area of fractured rock, which if you put a well in, you're able to pull a lot of fluid out of it. So this is just a natural spring, and I guess this is showing exactly that behavior. Very clear water coming over the lip at some speed, and it's clear and laminar up here, and as it goes downstream it breaks into this turbulent flow. So it's just like the hydraulic jump that you saw before. It's changing its elevation, same volumetric flow rate, but different characteristics of the flow. Shallow and fast upstream, and then slower and deeper downstream. So, and actually I think this line that you see going across there, not for that, actually probably is. It's probably for a slalom gate. In fact, I think you can see slalom gates. There's another line there. They're just vertical metal, not wooden. I can't see it. There were some. Yeah, actually it's there. It's very faint. They're usually striped. And so this one looks like it's white. They're always white and either green or red, and they signal somehow whether you should go into it upstream or not. And I suppose the one that's on the lip of the drop is perhaps a gate that's hung sometimes that you have to go over the drop, exactly where it is. So that's what we're going to chat about today. Greetings. You're not late, we're just getting going early. So this is what we talked about last time. So we talked about hydraulic radius and how we use that for Reynolds number rather than diameter, the characteristic length. We talked about uniform flow, gradually varying flow, and rapidly varying flow. And we talked about the Chezy, or the Manning formulae, which are, for this case, where it's the same depth as you go downstream as upstream. We wrote down these formulae. I guess perhaps the recap of the formulae is perhaps worth doing. They were that the velocity is equal to the hydraulic radius to the power 2/3 times the gradient of the bed to the power 1/2, I think. times this parameter k over n. This is a Manning coefficient, a big number if it's rough, a small number if it's smooth. This is a scaling number, which is 1 if it's SI units, and the formula comes out in meters per second, and kappa is equal to 1.49, I think it was, right? If it's in English units, in which case it's feet per second. And if you want to have volumetric flow rate, which is probably more interesting, then that is just the area times the average velocity. This is an average velocity, which is area times kappa over n, RH 2 over 3, S0 to the half. And so in terms of the geometry of this, S0 is just delta Z over L. So that was the outcome. And of course, the water on top of this will be doing this, where this is the depth of flow, which we'll call Y, and Y upstream and downstream are the same. So that's basically the relationship. We got to an example but didn't do it. Maybe worthwhile just looking at it quickly. Question is, calculate the flow rate in this system where you have this geometry. You know the height of flow. You know what the material is. It's either concrete or weeds, which would give you your Manning's number coefficient. And how do you calculate the volumetric flow rate? So this is the equation you use. It's in feet. You use this parameter here. You need to know the area. The area of flow is just this full area here, which is going to be 12 feet times 5 feet. 5 feet is the depth. 12 feet is the width, so the area of this part in the middle is exactly this. The portion of this is going to be, you can get these magnitudes from the trig functions. So if you know this here, this is going to be 5 feet, 10, 40. Or this is 5 feet, right? And this is 40. So it's going to be 5. This is going to be 40. 5, 10, 40, which is this, which is 5 feet. Is that right? What am I doing wrong? What am I not seeing? So 5 feet times 5 over tan 40, I guess is this, which is this. There's 2 of them. There's 1 here, and there's 2 here. So instead of being the half times this, it's 2 times a half, which is this. So the area is 89.8 feet. The wetted perimeter you can get from this magnitude, this length here, plus this length here, plus this length here, which is 12 feet plus 2 times 5 over sine 40, which is this length here. And so we have the area in the perimeter, so we have the hydraulic radius, which is just equal to whatever that is, 89.8 over 27.6. Has no dimensions because it's actually has dimensions of length, has dimensions of feet. And then the rest is just substitution. Constant because it's English units. Magnitude of the Manning's coefficient for weeds or concrete, I guess, is, I don't know where this comes from. concrete, either one of these, I guess. Is weeds in here, clean, gravelly, weedy, I guess is this. So one is 0.03 and one is 0.01, I'm guessing. Which are these? Different magnitudes for n values. And then this is just the hydraulic radius to the power 2/3, which is this term. This is the cross-sectional, no, this is the area. This is the hydraulic radius, 2/3. And this is the slope of the bed, which is every 1,000 feet, it goes down 1.4 feet. So again, that's a dimensionless ratio. And it comes out that the flow rates are whatever. By definition, the flow rates are going to be for velocities in feet per second, and for volumetric flows, cubic feet per second in English units, and meters a second and cubic meters a second in SI units. So straightforward. So that's that. So that was our recap. So there is no question on the final on that. But the stuff that is here on gradually varying flows, there is. And so we'll talk about gradually varying flows and what they mean. It depends on wave speeds, it turns out. And we can define Bernoulli equation into a specific energy equation, bless you, which is useful for us in analyzing this. So we talked about classifications before. Uniform flows, upstream and downstream velocity depths are the same. Bless you again. Gradually varying flows where it varies slightly from upstream to downstream, and rapidly varying flows would be things like a hydraulic jump that we just looked at in the video. This is just a repeat from previous. This is what we've done. This is what we would like to do today. So non-uniform flows. And this is kind of a recap, so we don't need that. Let's not worry about that. So it turns out that wave speeds are an important feature in understanding what these flows are. And so we talked about wave speeds maybe in the second time we met. We talked about an earthquake offshore in Japan in the Nankai Trough, that the wave speed, the P wave speed in rock is given by this expression here, which is just the bulk modulus of the rock divided by the density. We know that if we looked at in the atmosphere, you listening to me, you're hearing me at some wave speed, 600 miles an hour. We know that the velocity, the modulus of air or any gas, E gas, is equal to the pressure. And so we can substitute this with the pressure here. And we know that pressure is equal to rho RT. And so if you substitute in for this, you get rho RT, and you get, depending on isentropic or isothermal, this K value is 1 or 1.4. You get that the wave speed is equal to the gas constant multiplied by absolute temperature. That doesn't matter. And if you calculate what that is, we did, it comes out that it's, the modulus would equal 100 kPa, because that's what the pressure is. And you can calculate the wave speed to be something like 600 miles an hour. And so that's relevant to what we'll talk about, because in water, the celerity wave that we're interested in is the velocity at which a surface wave travels. And it's proportional to two, or it's controlled by two factors. One is the depth of the water, and the other one is gravity. So it matters which planet you're on. And I don't think there are any other planets with atmospheres that would have water on them except for Earth. And so the celerity wave speed is this, and we found out that maybe for a tsunami, it's of the order of 100 miles an hour. Quite fast, much faster than you perhaps think. And these numbers are all included here. And so the relevance of this is, perhaps I should do this, is it relates to how you get information to travel away from a location. And so the best example from this in common What did I just do? In common everyday life is the Mach cone. So the reason that commercial planes fly at 600 miles an hour, not 800 miles an hour, because 800 miles an hour is above the speed of sound. And so you have to use a lot of energy to fly at that higher rate, and you also have to build a sturdier plane. And the reason is that if you think about the rate at which sound waves can emanate from the tip of this plane, they can only travel as fast as they'll be carried by the speed of sound in air. If you're flying faster than the speed of sound in air, that energy given by that wave and the sonic boom can't get away from that. And so what happens is that you end up if you end up drawing a circle that represents where the plane's nose would have been a second before, 2 seconds before, 10 seconds before, then the distance that the sound wave has traveled in that time is the speed of sound times time since that was done. And so this Mach cone is a locus of all these circles, which are the ripples, if you like, trying to get energy away from the nose. And it means that you have to provide a lot of effort to push it through this. And it's the reason that you get a sonic boom that arrives from this. So the analog to that for us is this idea that the celerity wave, the surface wave, is trying to get away from the tip. I won't go through its derivation. This derivation just says that the celerity wave is actually quite good for what we'll do. It's not good for all waves. Sometimes when you have a wave train, there's a slightly more complicated formula, but for us, we can get by using this. Wave speed is just the square root of gravity times the depth of flow. And so for us, the reason for looking at that is that if you drop a pebble into a static fluid, the rate at which this wave will travel is the celerity wave speed. If you superimpose onto that static fluid a translation of the fact that the stream is moving downstream, and you do exactly the same thing, then you get two possible behaviors. One is that if the speed of the flowing water is less than the celerity wave speed, then you'll get this non-concentric series of rings. So imagine just dropping a stone after stone after stone in, and you'd get these concentric rings. This would be the earliest one, this would be the next earliest one, etc. But you'd have it trying to send information upstream, and it's not getting very far upstream. It's like trying to shout into the wind. If the wind is coming at you at 100 miles an hour and the speed of sound is 600 miles an hour, then relative to that, your voice is only being transferred at 500 miles an hour. If the wind is at 600 miles an hour and the speed of sound is 600 miles an hour, someone upstream can't hear you, never gets there. And so that's exactly what is here. The information that this is trying to send upstream, actually only moves more slowly if it's flowing at some velocity downstream. If this downstream velocity is larger than the celerity wave, then instead of looking like this non-concentric circles, they'll look like these individual drops. So this is the pebble that was dropped in at 0 seconds, 1 second, 2 seconds, 3 seconds, etc. And so the idea here is that no information gets transferred upstream, and so the form of the flow, which is here, the upstream flow has no way of knowing what that flow is. And so that's why we're interested in defining the flows relative to this Froude number. And the Froude number, or Froude number, is just the stream flow velocity divided by the celerity wave velocity. Where it's less than 1, it's called a subcritical flow. And so the flow is less fast than the celerity wave, and so information gets transmitted upstream. If it's greater than 1, then the flow is faster than the celerity wave, and no information can be transmitted upstream. And so the relevance of this is that this is the indicator that allows us to be able to say whether the flow will reorganize itself into one of these two behaviors, as in the hydraulic jump that we talked about. So it could be, for the same flow rate, it could be a very deep, slow flow, or it could be a very shallow fast flow. And these two will have the same volumetric flow rates, Q2 in each case, but they will be characterized by two different Froude numbers, because the Froude number by definition is the depth of flow for the velocity of the celerity wave, and the velocity of these two are different in these two cases. So that's what our job is today, to try and understand that. So what we'll do is we won't spend a lot of time on this derivation, but we'll try and use this information to try and figure out exactly how we characterize these different flows. So this is the idea. The idea is that we have a channel. That channel has a flow depth which is upstream and downstream. It has a slope of the bed which we've called S0, which we've called delta Z over L. And it has an elevation between upstream and downstream. And it has a velocity head upstream and downstream. And so this isn't any different from what we talked about before in Bernoulli. Elevation head, pressure head. If we're writing the pressures at this point here, the pressure head would be P1 over gamma is equal to Y1, right, at this point here. And P2 over gamma is equal to Y2. And we have a velocity head. So these are the three components of head. If we write Bernoulli, and Bernoulli has no friction in it, then this has to be the friction line. This means that we have a head loss. And so we can define this slope S sub F as equal to HL over L, right? This loss amount over this length. So this is just this slope. And so this is just classifying it. So if we write our energy equation of course is just Bernoulli. This is this equation here. Then what we can do is we can realize that we have these characterizations. We have the head loss defined in terms of this slope. So the head loss exists through Z1 and Z2. And so clearly we can define that in terms of the slope of the bed. The pressure head here and here we can define in terms of Y2 and Y1. And the V squared over 2G terms we have, and I guess the HL term we have defined here. HL is just going to be equal to, HL will be equal to SF times L. So if we make those substitutions, we end up with an equation that looks like this. This is the slope of the bed. This is the head loss term, which we have coming from here. And we can rearrange it. Don't worry about it. And we end up with this expression. So if we think about this in terms of Bernoulli, these two terms are our P over gamma term. These terms are our V squared over 2G terms. This is our Z term. And, sorry, that's not. This is our Z term. And this is our head loss term. Just written in a different way. And so we can, if this term here is equal to 0, we can get rid of it. If the head loss is 0, such as it would be in Bernoulli, and if the bed is horizontal, then we would get rid of this term, because 0 minus 0 is 0, and we'd be left with this expression. And so this is just Bernoulli, written in the case that we don't have any losses. And we can rewrite this by dividing it into upstream and downstream portions, just by writing it as Y1 plus V1 squared over 2G equals Y2 plus V2 squared over 2G. So this is Bernoulli equation written for an open channel flow. And we define each of these terms as the specific energy. This is the upstream specific energy, and this is the downstream specific energy. And they're equivalent. And so that's what this expression is that we'll deal with here. So it's just Bernoulli equation written in some way. So if it's written in terms of the velocities, which it is here, then that's not very convenient because the velocities are changing relative to the depth of flow. And so we might like to define it in terms of the depth of flow. And the one thing that we know is constant in the system, between upstream, even if the depths are changing, is this volumetric flow rate. And so what we can do is we can define the volumetric flow rate. But a more convenient thing is to define Q, which is the volumetric flow rate per unit width. So this would be meters cubed per second. This is clearly meters, so it'd be meters squared per second. And so if we manipulate this to define the volumetric flow rate as the velocity multiplied by the area, so B times Y is just the area. And so what we can do then is cross out these B's, and we just have Vy. So what we could do then is we could realize that V is equal to Q over Y. So if this is true, then this is certainly true as well, just by dividing both sides by Y. And so that means that now we could substitute this into our energy equation to deal with the upstream and downstream portions. I guess I don't want that. And so if you do that, if you substitute Q over Y into this, you just get Q squared over Y squared. So this term here is just our V squared term. And so now what we've done is we've written specific energy in terms of something that instead of a velocity that's changing between upstream and downstream is actually written in terms of a volumetric flow rate per unit width, which is the same upstream as downstream by definition, even as the depth of flow changes. If the depth of flow becomes less, then Q remains constant, but the velocity increases in direct proportion to how Y decreases. And so now what we can do is a little bit of math, is that if our specific energy is defined in terms of this, what we could do is we could subtract E off to the right-hand side, so it's all equal to 0. And we could multiply everything by Y squared. And that's what this equation is here. And that's just to illustrate the fact that this is a cubic equation. The highest power is Y cubed, and it has Y squared in it. Y to the power 1 doesn't exist. And so if this is a cubic equation that relates depth of flow, flow rate, and energy, then if we think about this, this has to have 3 roots. And so if we plot this equation, if we take a given value of flow rate, set Q, and if we change Y, so if we take Y equals 0, 1, 2, 3, 4, 5, 6, then we'll end up getting a result in terms of E, because E is our only parameter. So the curve, if we plot Y, depth of flow versus energy, E, will look like this. It looks like for a given Q equals constant, it will look like this. And then there'll be a portion below this axis. If you take a given value of energy, say on this curve here, then those exactly are the definition of the 3 roots of this cubic equation. This will be one root. This will be another root, and this will be a third root. Negative depth of flow makes no sense for a flow, so we don't care about this one. But we do care about these, because these are the two solutions to this equation that the flow could self-organize it to, which satisfy the equation, which means it can either be flowing at a very deep depth and very slowly, or a very shallow depth and very quickly. And so that's represented on this figure. I suppose the best way to illustrate that is to draw this. And so if you imagine a flow which is a weir, and if you imagine the base of the flow is here, and if you imagine that the individual flow velocities, flow depths are this, right? So this is our undershot weir. Upstream, we force it to be this depth, and this is the depth that we have, which is y sub. Subcritical flow, the Froude number, which is equal to the velocity of flow, what do we call it, Vs, streamline velocity, divided by square root gy, is less than 1. And that's this depth here. And this is our supercritical velocity, y sup, which is this one. And it turns out the dividing line between these is this nose of the curve. And so here the Froude number is greater than 1. So this is subcritical flow. This is supercritical flow. And they're divided by this, and actually this point here, the Froude number is exactly equal to 1, turns out. And so this is the transition. So this is the same flow velocity, same volumetric flow per unit width of the channel upstream as it is downstream, because if you take a section across the upstream and downstream, continuity requires that that's the case. It has the same flow. It has the same energy because we're not losing any energy in the system because we're satisfying Bernoulli. We've got a horizontal base, which means that S0 equals 0. We have no head loss in the system. So HL equals 0. So what we called SF, I think, right, is equal to 0. If you remember these equations here. These two equations here. This was the gradient of the channel, what we call the delta Z parameter, and this was the head loss due to energy loss, which was the HL component. If it's Bernoulli and a horizontal channel, these are both 0 together, so collectively they drop out, and that's exactly the case that we had here. So the energy upstream here has to equal the energy downstream, and so they have to be on the same energy line. And so that's all we need to know. What we could also do is we'd like to know as well exactly how we get this. I don't necessarily want to do, well, we can do the derivation. It's probably more useful to understand exactly how you might do the derivation. But the deal is that we have these two flows. We'd like to know exactly what this y crit value is. What's the critical depth at which this Froude number is between them, and what is the energy at which this occurs. It's the minimum energy. So what we could think about doing is we could take this curve that we have in terms of the depth of flow and the energy, and we could flip it on its side, I guess through 90 degrees, so we just write it so that it's the depth of flow and energy, and then we find out where the minimum of this curve is. So the minimum is given where the rate of change with y is equal to 0. We don't know whether that's a minimum or a maximum, but that is where the gradient of this is 0. If we differentiate this curve with respect, this is the value of E inside the brackets. If we differentiate it with respect to y, apparently we get this 1 minus q squared over gy squared. We set it equal to 0 because that's the gradient, and it turns out that this minimum value, this critical depth of flow, is equal to q squared over g, kind of as a standard result. And if we substitute this value of y sub c back into E, so E is equal to y plus, I'm just quoting it from here, q squared over 2gy squared. So if we take this y and put it in here and put it in here, then we find a standard result that at this point, which is here, the minimum energy is equal to the critical depth. Yeah, it's just putting y sub c in here, right? That's all. Is equal to this, and it turns out to be 3 over 2 times y sub c. So that's a standard result. So this is a standard result. Y sub c is equal to this is a standard result. No need to derive. And I suppose the energy equation as E1 is equal to E2. I'm going to screw this up, of course. Plus or minus L times S0 minus SF. SF minus S0 times L. And so for the geometries of that, well, you know the geometries. This is I don't know why. This is dz. This is L. So SF FSO is equal to delta Z over L. And the SF is equal to head loss divided by L, if you need it. But we've used it in the simplest form, where both of these terms we've assumed cancel out, and we only have to look at the energy upstream and downstream, and in which case we can do this. So that's kind of it. I don't know what else we have. I think we have some examples here. I didn't prepare much more than this. And I suppose if you choose a different flow regime, I guess what you don't know is if you don't have this constriction for flow within your stream, it could, if you know the amount of energy that you have in your system, it could organize itself as either one of these. And so you have to choose which one it would go between. If you want to move from this subcritical flow to the supercritical flow, then the only way you can get there is that you have to be on this curve, right? This curve represents a constant flow rate. And so if we go back to the movie, hopefully I didn't get rid of the one that I want. No, yeah, of course I did. Of course. If we go back to 303, the pen is too close to the pad. So if we go back to this, so this satisfies most of the criteria that we have. So this is flow from upstream to downstream. The base of this flow is flat, so S0 by definition would be 0. If we assume that there are no losses, energy losses in the system, so Bernoulli applies, then SF is equal to 0. And so now, spontaneously, we're going from this fast flow upstream at shallow depth to a slow flow downstream at deeper depth. It's doing it spontaneously, and so somehow it's doing that, and so it's not clear. Usually we have to have some kind of perturbation that makes it change that. And the easiest way of doing that, of course, is if we come back to looking at this, is that if the flow is constant along this curve, then to get from this upstream behavior that is supercritical, so this is a shallow flow, so I suppose if we drew that flow on here, it would be the opposite of this, right? It would be, if I extend the base of the flow here, then the upstream flow looks like this, and then it goes all the way up here. So this is the downstream flow, which is supercritical, and this is the upstream flow, which is subcritical. And so in it's the opposite, right? So this is, yeah, fine. So this is subcritical, yeah, fine. So it starts off with this. So to go from here, at the upstream, to go to here, it has to go along this curve, because at any point that we take along here, the flow rate per unit width has to be the same. This value is Q has to be the same. And so usually to be able to do that, we have to be able to supply something to do it. Here it's done it spontaneously because I presume that it's right on the edge of here. There's something that's pushed it through here. And we could imagine that thing that's done this is that the depth of flow that it's gone over has been some bump that's managed to push it along this portion here. It's changed the depth of flow by changing the critical depth. So I guess in this case it might have been a drop in the bottom, so that it's gone at the same flow rate to a deeper depth, which would be this y sub c. And as a result of that, it's been able to get through this nose, literally a nose, and be able to get to this other point as it goes downstream. And so the idea of that is that these transformations occur, but if it's the same volumetric flow rate that's going from upstream to downstream, there has to be something that kicks it over and perturbs the system in making it go from one state to another state, typically as it goes along this curve. And so typically it would be a change in the bed, although you don't really see it in that video. There's no apparent reason for that. And so that's how you might change from one upstream behavior to downstream. This is basically doing the same things. I'm not sure. Yeah, it's making the same point. So maybe this actually illustrates it quite well. And that is that if you have a flow that is upstream, so this is the reverse of our hydraulic jump. Instead of going from fast, shallow to deep, slow, we're doing the opposite. So up here we're starting off as a deep flow. We're doing something to that deep flow to get it to change. So the deep flow here, we could work out the energy for this. The energy upstream would be given by y plus, what's the term? Q squared over 2gy, is that right? So this would be y1, this would be y1, this is gravity. Just make sure that is the right equation for the energy. 2gy squared. This is a g. So we know the depth of flow, so we know y1. We know the flow rate. If there's a volumetric flow rate, this is already in, this is equal to Q, feet squared per second, not cubic feet per second. So we know Q, we know Y, we know the planet we're on, and so we have everything to be able to calculate E1. We could calculate this full curve by changing the values of Y sequentially, and we get values of E that would result from that, which would be this. And since we're at 2.3 feet, the depth of this is here. So this is the point that we'd be on this curve upstream. If we go through a depth where the change in depth between this top and this top goes to a depth of only 1.01 feet, which is this here, which is the location of this nose, then this forces this flow to go through this depth. So you can imagine going down the curve from this point here as you go up the front of this ramp. You get to this point here, which is this point here, and then now you're able to get to this final location, which would be at the same magnitude of energy, which would be this point here, which would be a depth of flow, which would be whatever this is. And I can't read this off, but this is going to be what Y2 would be. This flow here. And so you go from upstream, subcritical, downstream, supercritical. To get from subcritical to supercritical, you have to have some kind of way to get there by going down this trajectory, because the volumetric flow rate, or the volumetric flow rate per width isn't changing. This is the curve for all of those different depths. And so you have to get to this nose to be able to get through it. And then that's what changes you into a different flow regime. All right, I'm going to leave it there. So that's it. Good. All right. So no class on Friday, online. This just finishes off this. Tests next week. I would look seriously at the... I'm getting very lazy about remaking tests, so I'd look very seriously about the last 4 years from 2019 onwards. And so that's the... I'll include that on my posted video as well. So, any questions? Of course not.